Hello everyone. Today I'll talk about the solution to the problem smallest range covering elements from k lists. The first basic observation, and one that happens in many different problems, is that the only ranges that we should even consider are ranges that start and end at some value that appears somewhere within our lists. Both the left and the right. Of course, they can be from different lists, but the reason for it is that if we imagine our lists as maybe points, let's use 2 as an example, then if our answer was an interval like this, then surely we could push the left end forward until we meet some element from some list, and clearly we can push the right end left until we meet one element from a list, getting this interval, which is a smaller interval, but it has exactly the same set of elements within it. So this set is exactly the same. So both the start and the end has to be some point that we have as input. And this simple observation can already lead us to an idea for a solution, which will culminate in a sliding window solution. Because now, if we can take all the points that we have and put them as a single list, so we'll have to mark from which exact array the given value comes from. So let's say this one comes from 1, this one comes from 1, and this one comes from 1, those come from 2 or something. Then there are only quadratically many ranges that we have to check. If we can check in constant time, if a given range covers every list, then we have a solution that works in quadratic time. One way of, so we can, for instance, remember all the numbers that we've seen already, all the different numbers, the set of different numbers, and for a given range, if that set of different numbers has the length equal to exactly the number of different lists, then the range covers every list. And so if we can, for instance, for every left point, for every starting position, consider every ending position, then we can update this membership in constant time, because we just add the number that we've seen here. And whenever we see that, okay, we have one number for every list, then we know that this is the, so let's say that this is the first moment where you have both a 2 and a 1. So for this starting position, this is the shortest interval that contains an element from every list. And of course, this is a very standard pattern that, okay, we can do it in quadratic time by starting at every position and pushing forward until we reach the criterion or we run out of elements. But if we push the left end forward, it's impossible for the right end, for the optimal right end, to be to the left relative to what it was if the left end was to the right. More specifically, or maybe more, in a way, easier to picture. So if for this starting position, this ending position is the best, then if we push the left end forward, the starting position can never be pushed left. It might have to be pushed to the right, and indeed it has to be in this case, but that allows us to solve the problem in linear time, because now we can just go, and this is the two-pointer approach, we can go from the left, maintain the earliest point on the right that covers all the elements, and so now we have to, instead of a set, maintain a dictionary that will give us, so a hash map, for every list how many times it appears, and we push the right end forward until every list has at least one element within the range. Then we push the left end forward and remove this instance, so decrement the entry for 2 by 1. And now, for as long as we don't have anything from the list number 2, we have to push the right end forward. So this would be a linear time solution if we have that list ready. We don't have that list ready, so we can either just create that list and sort it for an n log n solution, or considering that all the lists are sorted, we can do it slightly faster, because we can create a priority queue. This is a very standard way of, this is a so-called k-way merge, right? So this is a k-way merge. Because if you have k sorted lists, then, and so you want to k sorted lists, transform them into a single sorted list, then always the next element for you to take is the smallest element from one of those remaining lists, and the smallest element from among all those smallest elements. The smallest element in any given list is the first element, so in other words, you have some lists, you want to merge them into a single sorted list. So you build a heap on the first element of every list, and you always take the smallest value. And after you take, let's say, this one as the smallest value, then this thing is in the heap. And then this is the smallest value, so you take this one, and this is the smallest value, you take this one, then this is the smallest value, you take this one. So you take it and push this one on the heap. So the heap will traverse all the lists, and in that way we can have it not n log n, but n times logarithm of k, which might be better if k is small. And also this approach that we have here can be used not just to perform a fast merge, to use this two-pointer technique. It can be transformed into a solution in its own right, and this is the solution that I have here. So we start by adding the smallest element from every list and create a heap. So for every list, we put on the heap its first element and its index, which is that it's from list of index, list index, and it's the 0th element. And to make a solution from that, we have to always remember the right end of the range we're currently looking at. So at first is just the maximum of all the minima from all the lists. And of course this taken list will be a heap. And we have to maintain the left end, and the left end is simply the smallest element on our heap. So this is the left end. So best at first represents the range that contains exactly the smallest element from every list. And now notice what we can do. When we have those elements, so at this point we have a range covering the element at index 1 from list 0, index 1 from list 1, index 2 from list 3. And now if we cross out, so this is the smallest element on our heap, and we cross it out, then if that new element is bigger than right, we have to update right to be bigger. And now our smallest element is again the smallest element on the heap. So if this was the smallest element, then maybe our smallest element will become bigger. And this is what we have to do for as long as we have some remaining elements from every list. So for as long as, well, whenever we cannot add the next element, then we know that it's impossible to cover all the lists anymore, so we can just break. So we go through in an infinite loop from which we'll break. We take the next element, so that next element has some value, it's on some list at position I, and we want to add the next element. If that next element doesn't exist, so if I is equal to the length of the appropriate list, we can break. Otherwise, we take the value of that element, we push it to the heap. So now we have changed our heap to have not this element, but this element, and we have to update the range that covers those three elements. So right becomes the maximum of the old right and the new value that we've pushed. Now the smallest value from among all of those representatives from every list is the 0th element of our heap. And since our heap holds triples, then we have to take the 0 value. And now if the right end minus this smallest element on our heap is smaller, so is better than the previous best range, we update the previous best range. We're being told that if ranges have the same length, then we have to take an earlier range. So that's why here it has to be strictly smaller. And at the end, so after we break out of this loop, we just return the best range that we've ever seen.